Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for February 28th, 2012.
On this week's show, laser radar could illuminate the way to deep space, a broadband polymer takes aim at handheld multispectral imaging, metal nanoparticles shine with customizable color, glass-based LEDs go UV, and a patent lawsuit crystallizes.
The European Space Agency is developing 3D imaging LiDAR, the laser equivalent of radar, as a navigation aid for exploring deep space. The wavelength of light is much shorter than that of radio waves, so LiDAR gives much more precise measurements. Laser ranging is already used for rendezvous and docking in orbit. For missions deeper into our solar system, ESA hopes to use 3D imaging LiDAR to build up a complete picture of targets such as a boulder-strewn surface that would work in total darkness or blinding sunlight. Terrestrial imaging LiDARs are much too bulky to use in space. The challenge is to produce a new class of imaging LiDAR much smaller and needing less power. Two designs aim at different guidance and navigation applications. A German-led unit demonstrates a future rendezvous sensor, while a British-led design is intended to help a lander touch down safely on a planet, detecting and avoiding hazards.
University at Buffalo engineers have developed a OneStep low-cost method to fabricate a polymer that, when viewed from a single perspective, reflects many different wavelengths of light. The material could form the basis of handheld multispectral imaging devices that identify the true color of objects. The portable technology could have applications ranging from home improvement, such as matching paint colors, to biomedical imaging, including analyzing colors in medical images to detect disease. The ease of producing the polymer could make it feasible to develop small devices that connect with cell phones to conduct multispectral imaging and improve clinical imaging in developing countries. The single-step fabrication method, shining a laser light through a curved lens, is affordable and relatively simple. The filter the researchers created was about 25 millimeters long, but the technique they used is scalable. It's possible to create filters of different sizes by shining the laser through lenses of different sizes.
Another new way to create and control color has implications for display screens and security tags. Engineers at Harvard demonstrated a new kind of tunable color filter that uses optical nano antennas to obtain precise control of color output. By precisely controlling the shape of the optical nano antennas, they can be tuned to react differently with light of different wavelengths and polarizations. Conventional RGB filters have one fixed output color, red, green, or blue, and create a broader palette of hues through blending. Each pixel of the Harvard filters, however, is dynamic and able to produce different colors when the polarization is changed. The advance has the potential for application in TVs and biological imaging and could also be used to create invisible security tags to mark currency.
A multinational team has developed a process for creating inorganic LEDs that produce light in the difficult-to-achieve ultraviolet range. The inorganic LEDs emit in the UV region thanks to careful design of nanocrystals embedded in glass. The material can then be integrated onto silicon-based electronic chips. Los Alamos National Laboratory's Sergio Brevelli and colleagues in Italy developed a fabrication process that amounts to a series of simple chemical reactions in a beaker. The work, reported in this week's Nature Communications, is a step toward biomedical devices with active components made from nanostructured systems. Such devices are desirable for medical applications because they are cheap to make, robust, and chemically stable. They can be used in harsh environments, such as immersed in solutions or implanted in the body. The approach is said to be scalable to industrial quantities with a very low startup cost.
The imaging unit of Zecotek Photonics has filed a patent suit against Sant-Gobain Philips. The lawsuit alleges that Sant-Gobain's LISO crystals infringe Zecotek's patent and that Philips infringes by using those crystals in its PET scanners. Zecotek's patent, granted in 2006, covers the substances and chemical formulations used to grow lutetium fine silicate scintillation crystals, which are characterized by their combined high light yield and ultra-fast decay times and are typically used in medical scanning devices.
Well, that's it for this edition of Light Matters. We'd like to hear from you. Tell us what you like or don't like about our program. Send your comments and suggestions to lightmatters@photonics.com.
You'll find links to share and subscribe to Light Matters by clicking the Share with Friends button on our video player.
Thanks for watching, and remember, it's only 5 minutes to enlightenment.
My job is to help medical surgeons, medical doctors, to see more than the eye can see using light. We have done a lot of work on image-guided surgery, which means you use the light getting at, for instance, an endoscope. You look at the tissue inside somebody who's being operated, and then you can diagnose what kind of tissue is where. So, for instance, we did a project where the prostate is removed and you want to preserve the neurovascular bundle. Neurovascular bundle is very delicate. If you damage it, then you lose your continency or you lose your potency or both. It's a very common problem with prosthetic surgery, and you know, 1 of 6 men will have somehow a prostate problem in his life. So it's a big issue. And we succeeded in finding spectral signatures that allow us to discriminate the neurovascular bundle better. And some of those spectral signatures are outside of the visible range. So by definition, the surgeon now cannot see them. And what we do is we add them to the image of the endoscope so that the surgeon can see them. It's digitally projected in the image, and that allows you to spare the nerve while you're doing the surgery, which will help to prevent the outcome of complications.